Okay, now same situation. This is at 0.4 meters, 0.6 meters. You got 200 of these things, and I've only drawn 3 of them. And I just want to analyze maybe what happens with 3 adjacent wires, current from 3 adjacent wires. Now, the 3 adjacent wires that I've got indicated here, the currents coming from those wires, aren't the same as these 3. So maybe I should draw more of these. I only drew 3 again because of resolution issues with the video being transmitted. But I can draw a whole bunch of these. And of course, again, I've exaggerated the scale here. This is much closer to the y-axis, and this is much further from the y-axis. But now we're just interested in what happens locally, and I'm going to pick just 3 of these that are ostensibly a millimeter apart, according to the model that we're using. And I'm going to look at how the field, the total field, arises. Well, from each of these, we have a field that surrounds the wire, and we have a field of uniform magnitude that's always at a right angle to the R vector to any point, so that the field is going to circulate in the counterclockwise direction in this case. Again, field out of the wire implies, or current out of the wire implies a field surrounding the wire in this sense. So what we have is these circulations of the field around each of these wires. You can see that in the middle here, halfway between this wire and this wire, the field from the wire on the right is down, the field from the wire on the left is up. The wires carry identical currents so that the fields are equal in magnitude. So these fields are going to cancel out. And the same over here. Okay, the downward field from this wire is equal and opposite to the upward field from this wire. They cancel out. We're not interested in what happens up here because we're not integrating over this line. We're integrating over this line, so we're interested in what happens below here. And what happens is fairly straightforward. We have the magnetic field of each wire being in this direction at any point on this wire, directly below. Now, the field from this wire at this point, because each of the wires gives rise to a field at this point, the field from this wire, if we were to draw the bigger circle, we would find that we get a tangent to that circle. So we get a vector in this direction. Now that vector is going to be much smaller than the one I drew, but I want to draw it big enough that you can see it. So we're kind of taking some liberties with scale. You can see that the field resulting from this current is going to be in this direction, and I don't have those directions exactly right. They're going to be much closer to the direction of this. Well, they're going to be much more nearly perpendicular to this one, according to the scale here. In any case, what we get at this point from these 3, we're going to have the contribution from this one, which is here. We're going to have the contribution from this wire, which is going to be like this, and I've used a red vector here to indicate that one, and a field from this wire, which is going to be in, actually I've got that wrong. This vector is the one that corresponds to this wire, and this vector is the one that corresponds to this wire. Again, I don't have the directions exactly right. There are all kinds of scale subtleties that we'd have to take account of, but we can get the idea that these 2 vectors are going to be symmetric about this vector just by the symmetry of this configuration, so that the vertical components, the z components in this case, are going to cancel each other out and leave us only with a y component, so that these 2 vectors are going to add up to a vector something like this. Again, according to the scale, this vector should be a little longer if it's going to represent the 2 vectors that I've indicated here. But we get the idea. We get a small contribution from these 2 currents, in the positive x direction, which is added to the larger contribution from this current, giving us a net magnetic field that adds this vector to this vector, giving us a bigger magnetic field in the x direction. And that whole argument tells us then, if we refine it a little bit, that the magnetic field along a horizontal line should be parallel to that line. Now, of course, this loop is inside, it takes up 0.2 of a meter at the center of a 1 meter span, so that all these symmetry arguments are going to work. And we get this result. Now, having gotten that result, we easily argue that the integral of B dot ds here, the magnetic field is horizontal along any line, the magnetic field along a horizontal line here is parallel to the line. Okay, so this magnetic field is in this direction. So to get the line integral over this part of the boundary here, this part of the boundary of our rectangle, the total line integral is just equal to the integral over the lower edge, because this is 0 and this is equal and opposite to this. And that's just going to be the uniform magnetic field that we get along here multiplied by 0.2 meters. And that's going to equal 4 pi k prime times our 60 amps. The current 60 amps being the current that penetrates this rectangular region by Ampere's law. And we then easily calculate the magnetic field. We divide this by the 0.2 meters, and we get this approximate result, 3,800 or so, and I'm approximating that as 4 times 10 to the negative 4th Tesla. And the units should be obvious. We have Tesla meters per amp multiplied by 60 amps. The amps divide, the meters divide, leaving us Tesla. So there's the magnetic field of this configuration.